So today is lecture 18 and we are potential well part completed. You mean the infinite potential well with the for the particle in a box? Yes, it was completed, and then after that we did the harmonic oscillator well. That was lecture 17. So today our goal is to go to the solution of the hydrogen atom, but first we discuss about angular momentum in quantum mechanics. So let's start classically. So classically, the angular momentum vector is given by r cross p, where p is the linear momentum mv and r is the position vector. Okay, which means that we have to evaluate a cross product. So these are the unit vectors. We have x, y, z from the r and px, py, pz from the momentum. Okay, so I can write the individual components of the angular momentum as Lx will be then ypz minus zpy. Ypz, sorry. Ly is x minus x. Sorry, zpx minus xp, and Lz is xpy minus ypx. So this is my classical expression in terms of position and momentum. And as you know, that you know the operators for position and momentum in quantum mechanics. So this is also my operator form for quantum mechanics. If I simply add a few hats. Screen froze. Oh, I'm sorry. So let me wait a few one or two seconds. Okay. I'm just putting hats on all the quantities: angular momentum, position, and linear momentum. Okay. Voice is so low. Okay. Let's pause for a few seconds. Okay, I hope is it improved enough? It's just some unstable. Internet. Can you hear me?
Ma'am, we can hear you, but I'm not sure if it's happening with others or not, but your voice is breaking at times.
Yeah, I think people have
Yes, ma'am.
different
Voice is
problems. So maybe
breaking.
just okay. Let's try for 2 more seconds. Not sure what to do. So what am I connected to? Am I still connected?
Yes, ma'am.
Okay. So I reconnected. Let's see. Okay, so the angular momentum operators, when you express the classical expression in terms of position and linear momentum, you can simply add the hat, and then you know what px, py, and pz are in quantum mechanics, and then you get the operators for the angular momentum. Now, are they Hermitian? So let's check. So let's check Lx. Can you hear me now?
Yes, ma'am.
Okay. So let's check if it is Hermitian. When you take a dagger on this expression, the order of the multiplication changes. So you have this. And the p's are Hermitian, the positions are Hermitian. So we get pzy minus pyz. Okay. And notice that this is the z component of linear momentum multiplied with y. So pz and y, they commute. We know that. So we can write this as ypz. So x and px don't commute, or and y and py don't commute. But when they are labeled by different axes, they commute. So I can reverse this order. Similarly for y and z, I have z py. And this is now the same as Lx. So this is equal to Lx. So this is commuting. Anyway, so now I show that Lx is Hermitian. Which also means that the angular momentum value is an observable. Similarly, this is true for Ly and Lz as well. So all Lx, Ly, Lz, they're all observable. The other thing we want to know about quantum mechanical operators is if they is what the values of their commutators are. So let's see if Lx and Ly commute. I'm not writing hats now anymore for the y and pz and everything.
Ma'am, how did we get that the y hat and pz hat commute exactly?
Because they're labeled by different axes. So it's z and del y. So those commute with no problem.
Okay.
Sorry, del z and y. So del z and y they commute because they act on different variables. Okay. So this is the commutator. Now I can do this in a short way and I can do this in a long way, like I told you before. So earlier, if you do the long way, you will of course.
Ma'am, voice is breaking.
It's again breaking. Okay, let's
Yes, ma'am.
shift my hotspot. Okay, so I've shifted to my hotspot. Can you hear me?
Yes, ma'am.
Okay. So let's see if this works out better. So this is so the long way would be to multiply everything and then so do an AB minus BA sort of commutator. But there are some relations of commutators which make this much easier to do. So if you have a commutator of A with BC, then this can be written as a commutator of AB multiplied with a C on the right, and then you can take out B on the left and have a commutator of AC left. Similarly, if you have AB as the first element of the commutator with C, then I can have a AC commutator and I take out B on the right, plus you have A, which is taken out on the left, and BC. So in case of operators, the order in which the various elements occur, that is the most important thing. So this is intuitive if you just maintain that the C will always come to the right of B and the B will always come to the left of C, but it can be taken out. So these are two relations we will use, and the other thing we will use is that the individual terms you can open out as commutators. So what I mean is that if you have a plus B and a C plus D, I think I showed this last class. This is A plus B comma C plus A plus B comma D, and then you can separate this further as A comma C plus B comma C plus A comma D plus B comma D. So these are some relations that we have. So let's use this last one first, and then we get ypz zpx minus zpy zpx. I'm just doing this explicitly to show you how the algebra works. You can do it in fewer steps if you recognize a few important things. And then you have minus y z x p z. Then you have plus z p y x p z. Okay. So y p z z p x. That we can use this relation or one of this, whichever one is applicable. This is yp z comma z, and I take out px. This is one term, and in the next term I take out y. This one. So this one is z px, and then I will take out z on the left, and I have y z px. Okay. In this term, you see, I will not write it any further. In the second one, you can take z out, and px and py, they are different elements, so they commute. So that will give me a 0. So I don't need that term. Okay. This one is I'll have to work out, and here again I have zpy and xpz. So I can take out z once and then afterwards x as well. And this will leave me with PY and PZ commutator. So basically, as long as the coordinates and the momenta don't have the same index, like none of the terms, then you can then those commutators are zero. If you like, okay, I'll then continue a few more steps and then we'll see. Okay, so this is the first one. Then I'll write this, the third one. The third one is oh no, here also, okay, here also we can already see it zero. So we take out PZ and then we have YX commutator. So YX commutator is definitely zero. So we only have the fourth one left, and that's this one. So here I can take out Z from the left, and I'm left with PY, X, PZ. And I can take out no, that doesn't help me. What I want is the, so here you see I have Z and PZ, so I want that commutator inside. So I will take out X. So I'll work on this term. So I'll take out X from the left, and I'm left with Z, PY, PZ. And I can take out now PZ on the right, and I have Z, PY, X. Okay, now let's again look at the commutators. So here I have the same index on the two terms, so that has to be worked out. So I can take out Y now from the left, and I have Y, PZ, Z, PX. In the second one, there are no common indices in the between the coordinates and the momenta, so that will be zero. In the third term, I have here Z and PZ, so that will remain. So I will have a plus X, Z, PZ, PY. Okay, that is a non-zero one. And here again, there are no common things, so that is zero. And then PZ-Z commutator is minus I H cross.
Ma'am,
Yeah.
why is the second and the fourth term becoming zero? I'm not able to understand.
This one, these two.
Yeah.
Yeah. So here you see, so the only commutators which are non-zero is XPX, YPY, and ZPZ. But none of those are possible from these commutators, because you see you have the coordinate index is Y, and the other two are Z and X. So those are all commutators between them are anyhow zero. So whatever the expression for it, it will be zero. So you can go one more step. I mean, you can take out Y, and then you'll have PZ and PX commutator, which is zero. And then in the fourth one, again, you see the coordinates are Z and X, and the momentum is Y. So no commutator involving these quantities is non-zero. But you can, of course, go one more step again here also. Take out Z, and then you'll have PYX commutator, which you know to be zero. Okay. So I'm just telling you that you can skip steps if you look closely. Otherwise, you work it out and you'll end up with the same thing. And then, okay. Did you get it?
Yeah, ma'am, a little.
Little bit. Yeah, so it's basically you're just looking at the indices and seeing if there is any possibility of a non-zero commutator coming from that term. Then you work it out further. If you see that, okay, there is no possibility of a non-zero commutator coming, then you can set it to 0 just straight away and not work it out any further. This is just to skip steps. It's not mandatory. But when you have lots of terms and lots of commutators, the more terms you get rid of early, the less chance of making mistakes. Okay. So here, okay. So let me just continue. So I have IH cross and I have XPY from the second term minus YPX from the first term. And that is equal to then IH cross. Remember where you've seen that expression, it's LZ. So this is now very interesting. So what were we working out? We were working out the commutator of Lx and Ly. And we ended up with the value of the commutator being IH cross Lz. That is very nice. So it shows that there's some sort of closure in this. So Lx Ly commutator is equal to IH cross Lz. And if you work out the other commutators, that is say Ly Lz commutator, that will turn out to be IH cross Lx and Lz Lx commutator will turn out to be IH cross Ly. So this sort of forms a complete set of interrelated equations, which is very nice. And similar relations occur for spin angular momentum. So similar relations occur for spin angular momentum operators, which are also simply called spin operators, by the way. And that is Sx, Sy, and Sz. Although they cannot be derived from classical physics. I mean, the spin has no direct analog in classical physics, but so they cannot be written in terms of xyz or px, py, pz or anything. But they have the same sort of relation. So it puts the usual angular momentum, the linear angular momentum, and the spin angular momentum on the same footing in a way, which is very useful. Mathematicians, in fact, they start out with these commutation relations. So here we showed how it comes about from physics. So this was like a specific case, but for mathematicians, if you tell them that there are two operators which have this sort of closed property, they can do a full analysis or a full algebra to solve equations and everything. Anyway, so that was just a side note, but okay. So these commutation relations will be useful for us. Now the next question that we ask is, can we have simultaneous eigenstates of Lx, Ly, and Lz? So the question basically is, if I put it in another way, is can we determine Lx, Ly, and Lz for a given system? So how can we answer that question? So let's say we can. Okay. So I have a state phi 0, and the action of Lx gives me a eigenvalue lambda x, and I get back phi 0. So a measurement of Lx will give me lambda x, a measurement of Ly will give me lambda y, and a measurement of Lz will give me lambda z. Let's see. Now let's start from what we know. So we know these commutation relations. Say or consider the action of the commutator on phi 0. Okay. So we know that Lx Ly commutator gives me Lz. Then if I open this out on the left, okay, and Lz acting on phi 0 we've said is lambda z phi 0. Then IH cross lambda z phi 0 is equal to then okay, let's do the first one. Okay, so Ly acting on phi 0 gives me lambda y phi 0. I have Lx left. And Lx acting on phi 0 gives me lambda x phi 0. Ly left. And that is equal to, now this is a number, so I can move this before Lx. And I end up with lambda y lambda x. Now Lx acting on phi 0 gives me lambda x phi 0 minus lambda x lambda y phi 0. So this is equal, so the value is 0, which implies that lambda z is equal to 0. Okay. Now if I use the other commutators, I can show that lambda x is also equal to 0 and lambda y is also equal to 0. So the only solution for the eigenvalues that I have considered, so for this set of equations, the only solution for, okay, let me call this A, the set of equations is lambda x equal to lambda y equal to lambda z is equal to 0. So that is basically a trivial solution where all the eigenvalues are 0. So there is no non-trivial lambda x, lambda y, lambda z for a non-trivial phi 0. So, therefore, simultaneous eigenstate of Lx, Ly and Lz is not possible. So now, since
Excuse me, ma'am.
Yeah.
Ma'am, actually, do we have to do all this to show this? Because earlier in one of the earlier classes, it was already said that if two operators don't commute, then they cannot have simultaneous eigenvalues. So
Yes, that is true. I mean, that is always true. So you can
So
directly
since we know
conclude
that these two do not commute, do we have to go through the whole thing? Or?
Well, you can consider this a verification. Then.
Okay.
You don't necessarily, yeah. So if you can use that argument, of course. I mean, whenever two things don't commute, they don't have simultaneous eigenvalues. That's true. And since you mentioned it, it's also true that there is even an uncertainty principle associated with the angular momenta. But that is normally not taught, and I will also not teach it. But if you are interested, I don't know if I've already done it, but I'll upload some notes on vLearn. So there is a uncertainty principle that you can get even from the angular momentum because they don't commute. Yeah, you don't necessarily have to go through this. That's true. You can consider this a verification if you like. Okay, but fine. So now that we know that they don't have a simultaneous eigenstate, then how many simultaneous things can we have? I mean, so two of these will never have a simultaneous eigenstate. No pair among them. So we have to look for something else then. So let's say I know one LZ, let's say, or LX, one of them I know, I found out. Is there some other associated quantity which can give me an simultaneous eigenstate? So this may seem like a unnecessary question at the moment. I mean, you might only be interested in the LX value, let's say. But it has some importance, so we will do it. So what other quantity can we measure simultaneously for the system? Or I can reframe the question: is there a angular momentum operator of some form which commutes with Lx, Ly, Lz? And why I ask this question is because there is a positive answer to this, and that is L squared. So the L square operator is basically Lx Lx plus Ly Ly plus Lz Lz, and this operator happens to commute with each of x, Lx, Ly, and Lz.
And is that because it is proportional to energy?
Not really. Not
I mean,
really,
L
but
square
that
by
has
2 omega, I think, is the energy, right? L square by 2 omega.
L square by 2 omega. Yes, L square has a dimension similar to energy. Because it is accompanied by a h cross squared, just like the kinetic energy, for example. So yes, you are right. It has the same dimension as energy, and that plays an important role in how we will solve the hydrogen atom problem. So you are exactly on the right track. But whether your cause and effect question is true, I don't think so.
Ma'am, is not it true that for any Hermitian operator, the operator and its any linear power, like not linear, sorry, and its any power would commute?
With it, yes, that's true. But L
Yeah.
square is not a power of Lx. Like individually, it's not a power of them, right? But you can, yeah. But since the commutator can be split into 3, yes, then you can. Yeah, that is true. Yeah, you're right. Yeah, you're right. So you can you can conclude that as well. So it will commute with so L square will, so Lx square will commute with Lx. Lx, but okay, but there is no guarantee that Lx will commute with Ly square or Lx with Lz square. No, that will not solve your problem. Sorry.
Okay, yeah.
That will not solve your problem. You will have to work it out. So let's work out one. I mean, it's pretty straightforward, not very difficult. So you have Lx and then Lx plus Ly plus Lz. Whenever I try to hurry, I make mistakes. Okay. So yes, so this commutator is 0 by your argument. Yes. But you have the other ones. And I am directly taking out 1. Okay. Because now I've shown you that you can do that. So I've taken out one Ly to the right and the other one to the left. And now the same thing for Lz. One Lz to the right and the other Lz to the left. Okay. and Lx Ly is IH cross Lz, Ly, then plus Ly, Lx Ly is IH cross Lz. Then you have Lx Lz, so our commutator was Lz Lx, so I'll have a minus sign, minus IH cross Ly Lz. And then I have again a minus sign, Lz IH cross Ly. Okay. So now I have Lz Ly and I have another Lz Ly, okay? So I cancel. Then I have Ly Lz and another Ly. Cancel. So this is 0. So they commute. Similarly, if you work out Ly L square commutator, Lz L square, all of them will turn out to be 0. So therefore, Lx L square equal to Ly L square equal to Lz L square equal to 0. Okay. So now we have established a few commutation relations, and we have the operator forms of the angular momentum in Cartesian coordinates. Okay, momentum. Now, the hydrogen atom, so like I said, we have an IE2 solving the hydrogen atom. This is a spherically symmetric system, and it is much more easily solved in the spherical polar coordinates. And angular momentum plays an important role in solving this. So we need the angular momentum operators in spherical polar coordinates. Okay. And we will also need the Hamiltonian of the hydrogen atom in the spherical polar coordinates. So we will have to painstakingly do both. For the Hamiltonian, it is not possible to work out in class, so I have uploaded the derivation there. I expect you to look at it, but you don't. It will not be asked in the exam. It's pretty long and tedious. But the angular momentum, I will work out at least partly now, just to explain how to do it. Okay. So the next thing we will do is angular momentum operator in spherical polar coordinates. So we have a coordinate system, Cartesian coordinate system, x, y, z. We have a point with the position vector r, and we want to express them in terms of the length r, the length of this vector, the angle it makes with the z-axis, which is called theta, and the angle of its projection on the xy plane, which is this. So this is the point which is projected on the xy plane, and the angle that it makes with the x-axis. Okay. So this is the definition of the three quantities, and then x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. And if I reverse engineer, then r is equal to root of x square plus y square plus z square. Theta is equal to cos inverse z by r, and phi is equal to tan inverse y by z. Okay.
Ma'am, it shouldn't be tan inverse. I mean, we should just write tan phi, right? Because if we go beyond pi by 2, the thing will change. So, I mean, the range of tan inverse is only minus pi by 2 to plus pi by 2.
Yeah, but anyhow, with position vectors, you're in the positive. Well,
I mean, our phi is from 0 to 2 pi, right?
your phi is from 0 to 2 pi. Yes, that's true.
So we shouldn't write as tan inverse.
Okay, if you like, I mean, you can put it like this as well. But when you solve it, anyhow, you will get two values for every phi, and then eventually you'll have to take a tan inverse. But okay, fine, no problem. If you want it like this, I don't mind. Okay. So then, I will do the simplest one. The remaining is simply a lot of like differentiation. So no use spending extra time. So I will evaluate del del phi. So del del phi is so phi is dependent on y and z. So I will have del y del phi into del del y. So this is the chain rule in partial derivatives. Then del x del phi del del x. Then since we know the expression of y, we can evaluate del y del phi. So del y del phi is basically okay, I'll write it here itself. R sine theta cos phi del del y, and then del x del phi is minus r sine theta sine phi. So this quantity is basically now x. So I have x del del y minus y del del x. Okay. And from here I can go over to the momentum. So this is, I can put minus 1 by h cross x py. So I'm converting del del y to py. And I have minus 1 by minus h cross y px. Fine. And I can rationalize this by multiplying an I. So I have I by h cross. Similar to the second term, xpy minus y px. That is equal to I by h cross Lz, which means that the Lz operator is equal to h cross by I del del phi. Okay. So this is the differential form of the Lz operator in spherical polar coordinates. So that only depends on phi. So this is the simplest one. Lx and Ly I will just write here, but it's the same procedure, just more algebra. del del theta plus cos by tan theta del del theta. Okay. And Ly is equal to, once again, minus cos phi del del theta plus sin phi by tan theta del del phi. Oh, sorry, this one is del del phi. Let me just check this one. So IH cross sin phi del del theta cos phi tan theta del del phi. Okay. Minus cos phi del del theta plus sin phi tan theta del del phi. Okay. Fine. And from these three, the L square operator can also be evaluated. Let's write it here for completeness. It's 1 by sin theta del del theta sin theta del del theta. Okay. 2 terms plus sin square theta del square del phi square. Okay. So if you evaluate now Lx, Lx into Lx plus Ly into Ly plus Lz into Lz, and you have to remember that you have to take a function always on which the operator will act, because otherwise you'll make mistakes because it involves the differential. Then you will be able to evaluate L square. Okay. So these are the angular momentum operator in spherical polar coordinates. Now, the trick that we will use for the hydrogen atom is that since Lx, Ly, and Lz commute with L square, we can find out simultaneous eigenstates of one of the Lx, Ly, Lz and with L square. So since Lz is the simplest operator, we will choose Lz and we will find simultaneous eigenstates of Lz and L square. So this will give me a set of functions which are candidates for being eigenstates of the Hamiltonian as well. Because the Hamiltonian also commutes with Lz, Lx, Ly and L square. Okay. So this will help us,
Ma'am?
Yeah.
Ma'am, how did you get these expressions for Lx and Ly?
Oh, I didn't work it out. I just wrote it. I just wrote out the answers in a way. So it's the same procedure as Lz, but you have to deal with a lot of trigonometric differentiation. So it's the same procedure, like this one. So you have to do del del theta. You have to find out del del theta, and then again work it out like Lz. So actually, I think I have already uploaded the solution actually to this. If I start to work it out, it will take me more than 2 classes. So I have the. So I found some notes and I have uploaded it on VLearn. So you can look at the derivation there.
Ma'am, so like do we need to practice like each and every step?
No, you don't need to do it. Like I told, this if I give it to you in the exam, the full exam, you'll sit doing only one expression. So this is not something that you will be asked. But I would advise you to memorize the Lx and Ly expressions just in case. I will try to avoid any question that involves them.
Ma'am, why not just print it along with the paper?
Yes, maybe, yeah. If required, I can print it with the paper, yes. Maybe that is a good idea. Yes, I'll do that if required. You don't need to memorize it then. LZ is simple. So LZ you practice, but and we'll only use LZ anyway. So this is just for completeness. I'm showing you LX and LY. And also because to find out L square. So L square we'll make a lot of use of. And L square I think you will end up memorizing because it has a pattern to it. And you'll use it several times. So L square you will learn up. And the solution of L squared is also there in the notes, I believe. I forgot which ones I wanted to upload. I think I've uploaded everything, so you will be able to find them. Okay, so let me just repeat what we will do. So we will find out simultaneous eigenstates of Lz and L squared, and then from those solutions we will look for solutions to the hydrogen atom Hamiltonian. Now, why that is the case is you'll figure out when you look at the hydrogen atom Hamiltonian in the spherical polar coordinates. They show a clear separation between a radial term, so something that depends only on the distance of a point from the center, from the nucleus of the hydrogen atom, and the rest depends on theta and phi. And this theta and phi part we will be able to simplify or almost get rid of by using the L square operator. So that is the next thing that we will do. And then the hydrogen atom Hamiltonian will be reduced, or the Schrodinger equation for the hydrogen atom will be reduced to a radial equation, and then we will only solve for R. But this will involve many steps. So we will save it for Tuesday, or let's see. Yeah, I will save it for Tuesday because then it will be fresh in your minds. I'll stop here for today. So do you have any questions from today or before? No? Okay.
Ma'am, actually, I still have I mean, you had clarified this previously also, but I'm still not, it's still not assimilated that, I mean, for the one-dimensional case, all the operators were clear, like x hat and px hat and those operators. But just my question is that for even for three-dimensional case, when we are constructing the operators, I mean, essentially we are just writing whatever we had written for the one-dimensional case, just like directly. So, I mean, and also we are saying that, for example, px commutes with py, and I mean, all the operators acting in one direction are not affecting the other directions at all. So, I mean, that is just taken. Directly. I am not quite understanding why that's allowed. I mean,
I mean, in a three-dimensional world, the motion in different directions, they are independent in the absence of a coupling potential, right? So here the operators are so let's see how to put it. So so I had explained it in terms of why they are independent in a physical system, and I had said that unless something is unless there is a field or something that changes let's say the position of the y direction changes the momentum in the x direction or something, this is definitely true. So this is in a physical sense, but the other if that is more understandable, you can think of it in a mathematical sense as well. So it's a differential operator, right? And it only involves one coordinate. So the px operator only involves a del x. So when it acts on a function which has various positions, then it will only act on its relevant coordinate. The rest is taken to be, the rest remains the same. Doesn't act on it, right? So the position of, so the x coordinate of the wave function does not affect the y component of the momentum. So you can think of it in that way also. So when you're evaluating it, so for every direction the operators are clear. And then if you want the total momentum operator, that comes from the momentum vector. So it has a x, y, and z component, and those individual operators are known. So they are, and they act, and there is sum. So there is no product. So that's why they are independent. Inside, let's say the kinetic energy operator, if there is a p square. When there is a p square, then there is again coupling. So a px, py does not necessarily commute with a py, px. So it's something like this. But as long as they are just the linear operator, they commute.
Okay.
Because when they act on a function, they only act on their own variables. They don't act on the other variables. That's why. So yeah. So okay, maybe actually the angular momentum can be helpful in that sense. In the angular momentum, for example, Ly and Lz, they don't commute, right? But a Py and Pz, they commute. So why is that? That is because the Ly operator, that is sort of it's a turning operator. So there is a cross product. So they're coupled. So the components are coupled. But in linear momentum, they are not coupled. Even physically, if you think about it. So whenever there is some sort of like very, very roughly speaking, or like there is some sort of turning going on, like in angular motion, then there is a coupling between the components. But in linear motion, the directions are independent. So that's why the linear momenta, yeah. So this is not a universal truth that the x and y components of an operator will always commute. But it's true for linear momentum and linear and position, of course.